I haven't heard anything, so hopefully you guys are there. Let me stop. Let me begin recording and share the screen. Come on. There we go. Beginning with Pasteur's works, discoveries included the relationship between microbes and disease. They suspected that microbes were capable of causing disease, and that became known as the germ theory of disease. And out of Pasteur's work came the development of immunity, that we have an immune system which protects us from foreign invaders, particularly microbes. And also out of his work came the work on the antimicrobial drugs. So all of that was due to Louis Pasteur. Getting started on the topic. Come on. A lot of discoveries happened after Louis Pasteur's work, showing that microbes came about through other microbes. First of all, Pasteur developed the basic idea, aseptic technique, and that you can grow microorganisms in a pure culture when you're using aseptic technique, keeping the culture pure. Koch then developed the technique for streaking for isolation on solid media. Louis Pasteur did have a procedure for getting a pure culture, but it wasn't very easy to do, and it was labor intensive. And Dr. Koch developed an easy way of getting a pure culture. And what you do is you streak the bacteria out on a solid media, streaking for isolated colonies. We'll talk about that later in the lab. And you do it 2 times, meaning you pass it through an isolated colony, pick from that colony, put it on another plate, streak it out to get isolated colonies, and then you pick from an isolated colony. When you've done that 2 times, the chance of getting a pure culture is really high. It's over 95%. And anyways, that was an important advance because now it was very easy for everyone to get a pure culture and work with cultures and microbes in the lab. Hess, at a year later, developed nutrient agar, a new solid medium for growing many microbes. And this was a general purpose media, meaning it allowed the growth of many microbes. It was actually nutrient agar. And then at this time, Sergei Winogradsky developed the idea that microorganisms were involved in various biogeochemical cycles, such as the nitrogen cycle that we talked about early on in this lesson. But it's also true that Sergei Winogradsky discovered the sulfur cycle, where bacteria were important in recycling sulfur on the planet Earth, moving it around from one form and one place to another. Pasteur then went on to show that microbes were responsible for fermentation. Alcoholic fermentation is the conversion of sugar to alcohol to make beer and wine. Pasteur got into this because the beer and wine industry asked him to find out what was spoiling their crop, meaning their beer and their wine. And he found that microbial growth was also responsible for the spoilage of food, particularly beer and wine. And the bacteria and the microbes were responsible for converting the grape juice to alcohol. But there were other microbes that were responsible for converting the alcohol to acetic acid, and that would ferment the wine into vinegar and not make it very tasty. And I'm not sure what it did to the beer, but it made the beer sour. Okay? Any question about any of that? So Pasteur showed that the spoilage bacteria could be killed by heat. And if you applied a heat that was not hot enough to evaporate the alcohol in the wine, you could protect the beer and the wine. And he called this process pasteurization, the application of high heat for a short time. It's actually used in a wide variety of foods. Most people are familiar with it with milk. But most beer, when you buy it in the store, you'll notice it's pasteurized. The exception is Coors beer. Let me think about that. I used to know this. Coors beer is filtered, and that's how Coors beer is allowed to be sold in most states, and that is, it is sterile because they sterile filter it, and then they bottle and cap it. And most places, they pasteurize the beer. And if you're not familiar with Coors beer, it tastes a little different than the other beers which are pasteurized. And I've never had raw milk, but I've heard people who did, and they said that raw milk tastes different, and they said it tasted better than pasteurized milk. So pasteurization can affect the taste. Okay? With the work on fermentation, that microbes can affect organic material and then change it. Out of that work came the concept that microbes might have a similar relationship with plants and animals, and that microorganisms may cause disease. This concept is known as the germ theory of disease, that germs cause at least some diseases. This was an important advancement in science because before that, people thought, and I'm talking about the medical profession, that poisonous vapors were responsible for some infectious diseases. For example, people got cholera from walking through a swamp and breathing in the poisonous vapors. It wasn't because in the swamp there were microbes that could cause cholera. And the germ theory of disease changed that and said, no, we believe that germs, microbes, can cause disease. There's a number of work on the germ theory of disease. I'm going to have you read about it. We're a little behind schedule, but Semmelweis and Joseph Lister introduced aseptic surgery, or sterilization, in the medical profession, and initially it was rejected. Like Semmelweis was actually fired by the president of the hospital because he was insulted that they were suggesting the doctors wash their hands before they engage in surgery. The germ theory of disease was finally proved by Robert Koch. And by the way, I am probably pronouncing his name incorrectly, and that's because the English do not have a way of pronouncing CH. It's like a hard X, and the English, we just don't say that sound. And anyways, Dr. Koch proved that the bacterium Bacillus anthracis caused the disease anthrax. And then he wrote up the procedure he used, the experimental steps required that a given microbe caused a specific disease. And these steps are known as Koch's postulates. And this proved the germ theory of disease because he showed a bacterium was capable of causing a disease. Okay? Any question about any of that? This is the first time we'll talk about Koch's postulates in this class. We'll be talking about it in 3 places in this class. So obviously this is a major topic, and we'll return to it 2 more times. Edward Jenner also was important in this, and he's the first person who came up with the first vaccine. He inoculated people with the cowpox virus and then noticed that the people were protected against smallpox. However, no one during his day understood why smallpox was protected by the vaccine, meaning why was cowpox protecting against the disease smallpox? And this was not understood until Louis Pasteur did some work on vaccines, and he showed that the reason why cowpox protected against smallpox is that the two viruses were similar. And then when the immune response occurred against cowpox, some of that immune response carried over and attacked smallpox. Okay? Any question about that? With Louis Pasteur's work, people now understood why vaccines worked and how to go about making vaccines. And since Edward Jenner's time, there had never been another vaccine until Louis Pasteur's time. You don't need to know this, but Louis Pasteur did his work on vaccines on a disease that caused chickens to get sick. So it was a virus that infected chickens. But then he went and did other vaccines, and I can't tell you all the vaccines he did. He's most famous for rabies. He came up with the rabies vaccine. The word vaccination is actually derived from the word vacca, which is a word meaning cow. I think it's Latin for cow. And that's coming from the cowpox virus being used as a vaccine against smallpox. And then the protection that we get from a vaccine is called immunity. Any question about any of that? Chemotherapy is, broadly speaking, the treatment of disease with chemicals. Now, in today's terminology, chemotherapy is used almost exclusively with a drug that is used to treat cancer. But strictly speaking, the term is a treatment to cure any disease with a chemical. And a chemotherapeutic agent is one that is used against infectious disease. And as I stated, you can have a synthetic drug where a human makes it, or you can have a drug that is made by a living organism. And in your textbook, that is called an antibiotic. The term antibiotic in the textbook means specifically a drug that is made by a living organism that inhibits the growth of other microbes. Now, that is a textbook definition for the term antibiotics, and that would mean that penicillin G is an antibiotic, but carboxycillin and even ampicillin, which was an early member of the family, is not an antibiotic. Okay? I won't use the term antibiotic that way because it's not used that way in the general population, and it's not used that way in the clinics as well. An antibiotic is a drug that is used against a microbe. That's the way it's used in the general public as well as in the clinic, and I will use it that way. The first drug that was actually used, at least in the West, was quinine, which came from the bark of the cinchona tree, and it was used to treat malaria. Does anyone want to guess when quinine was first used in Europe to treat the disease malaria? Take a guess. Nobody wants to guess.
1920.
1920 would be a really good guess because we're talking in the early 1900s. But no, you're wrong. It was actually in the 1600s. Okay? And they didn't keep good records right back then. And that's why we're not sure exactly when Europe started using quinine, which back then they just used the bark of the cinchona tree, and I don't know how they consumed that, but it was used in the 1600s, maybe around 1650. The Jesuit missionaries in Peru noticed that the natives of Peru, meaning the Indians of Peru, were taking the bark of the cinchona tree to treat their malaria. And the missionaries noticed it was successful. And so they reported it and sent the bark of the cinchona tree to Europe. And this was the first chemotherapeutic drug, or you could say antimicrobial drug that was available, at least in Europe. And that was quinine. Paul Ehrlich, out of Louis Pasteur's work, theorized that it would be possible to find a chemical which one could use to treat a disease. And he started looking at different chemicals and testing them to see if they would cure disease. What he used was syphilis that he was growing in rabbits, and then tested one chemical after another to see if he could find one that would cure disease. And he called this a magic bullet, a chemical that could be used to cure disease. And in 1910, he actually found one, a synthetic arsenic drug, salvarsan, which cured syphilis. Okay? Now, the people in his lab put a sign above his door, "Abandon all hope, ye who enter here." And that's because it was very tedious to take one chemical and then test it on the rabbits, and then test the rabbits to see if they had syphilis or not. And they just went through drug after drug, and about drug number 500 was where he found the first magic bullet, a chemical that could be used to treat a disease. Now, this drug, salvarsan, was fairly toxic to people. Remember, it's a synthetic arsenic drug, and wives have known for ages that arsenic was something you could give your husband to get rid of him. Okay? Any question there? That's sort of meant to be a little bit of a joke, so don't take offense at it. Meaning arsenic is a toxic poison, but it was more toxic to syphilis than it was to the patient. The first discovery of antibiotics came with Alexander Fleming in 1928, and he was actually a sloppy microbiologist, and he got contamination of his plate. So he streaked out the bacteria on his plate and then came and looked at it later, and he saw that a fungus was contaminating the plate. But he noticed that there was a region near the fungus where the bacteria did not grow. And that zone of inhibition, Alexander Fleming correctly concluded, was something coming out of the mold colony and preventing the growth of the bacteria. And Alexander Fleming worked with that and tried to show that it was an antibiotic, but he was never ever able to purify the antibiotic. All he was able to do in the 1920s was get a crude extract of the growth medium that he was growing the mold in. and that would be something you could not give the patients. I don't even think he had it filtered to keep out the mold. And the mold happened to be Penicillium with an M, and so he named the antibiotic penicillin. And specifically speaking, it's penicillin G that he discovered. Now, the first antibiotic that was available clinically to be used in the clinic or the hospital was actually a sulfa drug, sulfonamide, and it was man-made in 1935. And because it was man-made, it was pretty easy to purify and then give to the patients. So sulfa drugs were the first antibiotic that clinically became available. Penicillin was the second antibiotic that became clinically available, and it was purified in the 1940s during World War II and tested clinically en masse. And if I have time, you guys should ask me about the story of the first two patients who were given penicillin, okay? And we'll talk about that. I don't have time today, but if I have time, ask me about the story. It's kind of a, I don't know, educational and amusing story. All right, when we're talking about microbes, bacteria were once classified as plants. Hence the term flora or microflora was used for microbes. That has now been replaced by the term microbiota. But when I went through college and took microbiology, the term microflora was still used. So if I use that term, please correct me and say, you mean the term microbiota, all right? Because, I don't know, sometimes I just say the old term, which is no longer used. When we use the term normal microbiota, we mean the microbes that are normally present in and on a host, a person. And animals and plants host a symbiotic microbial community where there are many, very many microbes living in symbiosis with the host. And the normal microbiota are central to animal and plants' welfare. And we'll talk a little bit more about that. So the normal microbiota are found on and in the skin, in the oral nasal cavity, in the upper respiratory tract. They're not usually found in the lungs. They're found throughout the digestive tract, and they're found in the urethra. The normal microbiota are not found internally, such as in the blood, in internal organs and tissues. But the normal microbiota are helpful to us because they can prevent the growth of pathogens. They can compete for their resources, preventing the normal pathogen from getting food and other resources. They can also compete for the pathogen for space, like if my skin is coated with microbes, which it is, and a pathogen were to get on my skin, it may not have any skin surface to, colonize as its home. And that's because of the normal microbiota. The normal microbiota can secrete toxins that inhibit the growth of pathogens, and we'll talk a little bit about that later. And the normal microbes are important to us because they can help us digest our food, like E. coli does that. They can help us produce nutrients and growth factors. For example, humans get a significant amount of their folic acid and vitamin K from their normal microbiota in their gut. And I've already talked about digestion, how the normal microbiota can help us digest our food. Any question about that? With cows, they would not be able to digest grass if it wasn't for their normal microbiota. The cow's stomach cannot digest grass, but in their stomach they have a normal microbiota which can produce the enzymes that are required for digesting grass. And by the way, you should not eat grass because we do not have those normal microbiota. The normal microbiota do not normally cause disease. However, they can cause disease under certain circumstances, such as an immunocompromised host, like an AIDS patient or a patient receiving chemotherapy. An infectious disease is when a pathogen overcomes the host resistance and then causes disease. Infectious diseases are caused by a pathogenic microbe. So an infectious disease is always caused by a pathogenic microbe. All right? Any questions there? Remember, most microbes do not cause disease. But those that do, we call them a pathogenic microbe. An emerging infectious disease is a new or changing disease that is increasing or has the potential to increase in incidence. Right now, we're under the pandemic of COVID-19, and that is considered an emerging infectious disease because 2 years ago, nobody in the human population was infected, that we know of at least, with COVID-19. All right, so I want you to know what an emerging infectious disease is, and that's all you need to know about emerging infectious diseases. I have assigned the reading on this topic, and there's more slides, but you will not be tested over emerging infectious diseases, except for what the term is. Any question about any of that? If not, let's move on to Chapter 2. So normally, when I give you a slide presentation, the first slide I will give you the major goals and the rough outline. You should always know the major goals and the major terms for the lesson. But if you want to know all of the objectives for the lesson, you should look beyond this slide here. You should look under the study guide. Let me see if I can call that up. For the lesson. And the study guide, I don't have it, sorry. No, I don't have it. The study guide you can find in the page on Canvas. And at the top of the study guide will be all of the objectives. If there's any question, ask me on another day when we're not so rushed. So know the terms and also be able to describe the 4 major biological molecules and be able to describe the relationship between these molecules and the characteristic of the molecules and how the large ones, the polymers, are made up of smaller molecules called monomers. And that is true for 3 of the major biological molecules. And these are also called the molecules of life, and those are carbohydrates, proteins, lipids, and nucleic acids. and carbohydrates, proteins, and nucleic acids, all of the polymers, the big molecules, are made up of monomers. For the lipids, some of the lipids, meaning a polymer of a lipid, is made up of monomers. But not all of the lipids are made up of monomers. Is that clear? All right, there's no questions. Let's move on. Be able to describe the composition, structure, and function of the 4 major biological molecules, and then be able to give an example of each. Any question about all of that? All right. If not, let's just talk about the scale of things. You do need to know the scale of things. Let me blow this up. And this chart is showing you the scale of things. So you don't need to know the size, like a human is on the order of 10 meters. That seems a bit high, actually, but we'll go with it. Oh, there's human height there, closer to 2 meters. Anyways, a human, you should know, is bigger than an egg, and we're talking about a chicken's egg, which is bigger than a frog's egg, which is bigger than a eukaryotic cell, and the biggest eukaryotic cell in the human body is the human egg, meaning the oocyte. And a eukaryotic cell is bigger than a prokaryotic cell, which is bigger than a virus, which is bigger than a large molecule like a protein, which is bigger than a small molecule like water, which is then bigger, which isn't shown there. It's bigger than an atom. There you go, atoms. So you don't need to know the sizes here, but you should know the relative ranking. And there's an error in this chart, which is really unbelievable because it was in the textbook for many publishing of the textbook. It's got 1 micrometer twice. It should be a micrometer here, but right there, that shouldn't be a micrometer, that should be a millimeter. Okay? And I'll show you that in the future where I've even got it changed. But there is one error in the size here. All right, any question about the size of things? When we're talking about chemistry, you should realize that organic compounds are typically complex structures held together by carbon, and the carbon holds it together with a covalent bond, and carbon can bind to 4 other atoms. Okay? Inorganic compounds typically lack carbon, although they don't always lack carbon. And inorganic compounds are required by living organisms for growth, repair, maintenance, and reproduction, but they're generally simpler than an organic compound. Some examples of an inorganic compound is, of course, oxygen, water, and carbon dioxide. And you'll note that carbon dioxide doesn't lack carbon. Okay? And it is an inorganic compound. Organic compounds are chemically more complex, and we'll talk about them later in the lesson. So I'll give you an example of an organic compound later in the lesson. All right. Is that next? Yes, all right. So when we're talking about inorganic molecules, one of the most important in the living body is, or a living cell, is the water molecule. Water is a polar molecule. When I say it's polar, that means the electron that's holding the hydrogen and the oxygen together is not shared equally. And that's actually 2 electrons shared between hydrogen and oxygen. Oxygen pulls on those electrons more than hydrogen, so oxygen has the electrons more of the time than hydrogen. Now the electrons move, and we're not going to talk about that, but they're around oxygen more than they are around hydrogen. And that makes oxygen partially negative. Now your textbook doesn't discuss that as a partial charge, but I discuss it that way. And then the electron is away from hydrogen more than it's present during hydrogen, and that gives hydrogen a partially positive charge. And the oxygen has a partially negative charge because the electron has a negative charge. The polarity of water allows water to form hydrogen bonds with other polar molecules. And this can be water or sugar. And here I'm showing it here. This is water. And the positive charge of one water molecule can be attracted to the negative or partial negative charge of another water molecule. And that electrostatic attraction between the partial positive charge and the partial negative charge, we call that a hydrogen bond. So water has 2 chemical bonds. Between water molecules, we find hydrogen bonds. And I'm talking about liquid water or solid water. As in gas, you don't have the hydrogen bond forming. Okay, but in liquid water you do. And the other chemical bond is inside the water molecule, and that's a covalent bond holding the hydrogen together with the oxygen. All right, so with the water molecule, it has 2 chemical bonds, a covalent bond within the water molecule, and then a hydrogen bond between water molecules, at least when we're talking about liquid water, or it's true when we're talking about ice as well. Any question about that? Water is a good solvent because all polar molecules and then ions can dissolve in water. Like salt is an ionic molecule, and water comes up to the sodium, which is positively charged, and then we'll pull it out of the sodium chloride crystal, and then the negative portion, meaning the oxygen portion of water, will be oriented towards the positive charge of the sodium ion. And then for the chlorine, it'll be pulled into solution, and the positive hydrogen will be oriented in water towards the negative chloride ion, so that these ions can go in solution. So they'll be dissolved in the water. And if you've ever put a little bit of salt in water, the water will dissolve all of the salt until you get the water to 30% sodium chloride. After that, the salt will no longer dissolve in the water. Okay? So polar substances and ions dissociate in water, and we call that a solute, where the sodium ion is in the water solution. And water is called the solvent, and we'll talk more about that later. Polar molecules are hydrophilic. And what does that mean? It means literally love water. So polar molecules love water, meaning they will dissolve in water. Non-polar molecules are repelled by water. We use the term hydrophobic, which literally means fear of water. Philic, love, water. Phobic, fears water. and nonpolar molecules do not dissolve in water. An example of that is when you mix vinegar, which is mostly water, with oil to make your salad dressing, and then you shake it up. The nonpolar molecules will separate from the water molecules, and that's because the oil is hydrophobic. The acetic acid in the water will be hydrophilic, and the acetic acid is what makes vinegar. Okay? Any question about any of that? Hydrogen bonding between water molecules makes water excellent at buffering the temperature. Water absorbs a lot of heat before water absorbs the heat in two ways, and that is when a molecule gets a higher temperature, it means the molecule is moving around and vibrating more than it is at a lower temperature. And that is actually what the temperature is, the speed of the movement of the molecules. Any question about that? Water, when you heat it up, it is true that the water molecules vibrate and move around more rapidly, but besides that, some of the energy from the heat can be taken by the hydrogen bonds formed between the water, and you need energy to break those hydrogen bonds. So before the water will start boiling, you have to give enough energy to heat up the water molecules so they'll move, as well as put energy into the hydrogen bonds to break those bonds. And when the water molecule has all of the hydrogen bonds broken, that molecule will evaporate. Okay? And leave the liquid solution that we're calling water. So when water molecules break off, it's also the water molecules that have the most energy that leave, causing the water to evaporate. And that takes away the majority of the heat, because the molecules with the most energy, the water molecules with the most energy, are the ones leaving the water. Any question about that? And that is why water, when you perspire, is a good cooling agent, because the water will evaporate, cooling you, and then the water molecules, which are the ones leaving, are the water molecules with the most energy. And that is why when you perspire, you cool. All right, any question about any of that? Anyways, why water is good at buffering the temperature is because water is a substance that can absorb heat in two ways. Most substances like metal or oil can only absorb heat, and then the temperature will be elevated as the molecules move around more rapidly, and that causes the elevation in the temperature. But with water, you get that happening, but you also get some of the heat energy going into breaking the hydrogen bonds. And so because water can absorb more energy than most other substances, we say it is excellent at buffering the temperature. For those of you in Western Oregon and Washington, the reason why we have such a mild climate is because we're near the Pacific Ocean, and the Pacific Ocean, all that water helps buffer the temperature. Any question about any of that? All right. Water can split apart, and when the water molecule breaks apart, it will break into hydrogen plus ion, meaning a proton that lost its electron. The electron will be on the OH group, and it'll have a negative charge, and then the hydrogen has a positive charge. The charged molecules can then participate in chemical reactions. So why water can carry an electric current is because some of the water breaks apart into H plus ions and OH minus ions. However, distilled water is not as good as water with dissolved minerals in it at carrying an electric charge. So it's really the minerals in the water that are responsible for the electricity being carried by the water. And what I'm talking about is you're more likely to get a severe shock if somebody has an electric probe put into the water and you stick your hand in it. You're more likely to get a shock, and a stronger shock, if you have minerals dissolved in that water as opposed to distilled water. Anyways, when water breaks apart, it also gives water its pH. Let me shrink this. Here we're looking at a pH scale. It can vary between a pH of 0, very acidic, and a pH of 14, extremely alkaline. Lime water, which is an oven cleaner, is very acidic. The stomach acid, actually the acid in your car, is very close to pH 0. It's around pH 1 or less. Stomach acid is between pH 1 and 2, although it depends on what you eat. It can go up as high as 4. What the pH is the amount of hydrogen ions in solution. Let me see if I can blow this up a little. Neutral water has a pH of 7, and that means that there is one hydrogen ion produced in the water, meaning water breaking apart in H plus and OH minus. There's one hydrogen ion in 10 to the 7th water molecules. Now a slightly acidic solution, like a pH of 6, has one hydrogen ion in 10 to the 6th water molecules. And as you become more acidic, the number of hydrogen ions increase until you get a pH of 1, where there's one hydrogen ion in 1 to 10 to the 10th to the 1 water molecules. So that would be 1 in 10 water molecules. One of the water molecules will break into H plus and OH minus. Note, when we're discussing the pH, we're only talking about the concentration of H plus. We're not talking about the concentration of OH minus when we're talking about pH. Any question about that? And then conversely, an alkaline solution like seawater is above pH 8. That means there's one hydrogen ion in 10 to the 8th water molecules, or more than 10 to the 8th. Any question about any of that? All right, so this is a pH scale, and you can see that anything from 0 to 7 is acidic. Stomach acid, lemon juice, grapefruit juice, tomato juice. Milk is slightly acidic. Pure water, freshly distilled water, will be a pH 7. The blood is very slightly acidic. Seawater is slightly, not acidic, alkaline. Seawater is more alkaline. Milk of magnesia is alkaline. Household ammonia is alkaline. Household bleach is really alkaline, and that's probably the strongest alkaline everyone's had contact with. Some of you, if you've used oven cleaners, that would be the strongest alkaline that you've handled. let's briefly talk about acids, bases, and salts. An acid is a substance that, when it dissociates, gives off H plus ions. So when we have HCl and put that in water, the HCl can dissociate into H plus ions and chloride minus ions. And this will be an acid solution from increasing the hydrogen ions in solution. Now the textbook says a base is a substance that dissociates and gives up OH minus in solution. Like sodium hydroxide, when you dissolve that in water, will release the hydroxide ion, which is basic. Okay? However, you should know that bicarbonate and carboxylic acid are basic because the sodium bicarbonate, so that carbonate can absorb hydrogen ions and then make carbonic acid, and that will be a solid, and that will absorb hydrogen ions from solution, so we call bicarbonate a base. And this isn't in your textbook, but bicarbonate is clearly a base because it absorbs hydrogen ion. So you should know that a base is something that dissociates hydroxide ion, or a base is something that absorbs hydrogen ions. Like bicarbonate absorbs hydrogen ions. Any question about any of that? And by the way, this is the major buffer in your blood. Carboxylic acid or carboxylic acid and bicarbonate. You can lose the hydrogen and get carbonate, but that's not very likely to happen in your blood. All right, any question about an acid and a base? If not, let's go on to slide 10 and talk about what a salt is. A salt is a substance that dissociates into cations and anions. A cation is a molecule that has a positive charge, an anion is a molecule that has a negative charge, and a salt is, or the cation and the anion is neither H plus or OH minus. So sodium chloride, which everyone calls salt, is a salt because it dissociates into the sodium anion and a chloride anion. But we could also say magnesium chloride too is a salt because it dissociates into cations and anions. Any question about that? An electrolyte is a molecule which can dissolve in water, and when it dissolves, it dissociates into cations and anions so that it can conduct electricity. And for example, sodium chloride, when it dissolves in water, there will be sodium and chloride dissolved in the water, so that sodium chloride water, meaning salt water, is an electrolyte. Any question about any of that? If not, I think I'm going to stop here so that we can start with the lab, which I believe starts at 6:30. Is that correct? Let me get it here. Yes. So I want to stop now, and we will continue with this lesson in the lab. Are there any questions? If not, I'll see you at 6:30.